Lesson 33, we're going to talk about the definition of a parabola. So this slide is actually the very last page of this lesson. This is the lesson summary. This can be found on page 179 of your notes. So I would recommend you first take a minute and turn to page 179. So that way you could see these definitions and see this exact same image that I'm going to talk about without having to redraw it. So in this case, we're going to talk about what it means to define a parabola. And so in this definition, they say a parabola with a line which is called a directrix. So we'll underline that key line. And then a focus point, which we'll call F, is the set of all points in the plane that are equal distance from point F and point L. And what they're talking about in that idea is, if we were to highlight a couple of things in that note, here we have the directrix here at the bottom, right there. And then at this point location right here is our focus. And so this definition says that if we have a directrix and a focus, which is defined by L and F, then if we were given a random point, and so this random point is over here at XY, that the distance from the focus to this random point is equal to the vertical distance from this point straight down to this said directrix. So these two are congruent. That's what we're going to work with today, is this level of congruency between these two lines that are illustrated. The goal behind that is to basically use the distance formula. So the distance formula, D equals the difference of the x's squared plus the difference of the y's squared, and then square root all of that. We want to be able to convert that into a y equals ax squared plus bx plus c quadratic that is going to detail this particular curve, this quadratic curve right there. So another couple of definitions: axis of symmetry, we've heard of this one before. The axis of symmetry is the line in the parabola down the middle. It goes through the vertex, and the goal is to create a left-hand side and a right-hand side that is equal in every single way, just on opposite sides of the axis of symmetry. The vertex of the parabola, we've all heard that before, that the vertex is either the lowest or maximum point of a parabola. It is the point where the axis of symmetry goes through. It's also the turning point from where a parabola goes from increasing to decreasing or decreasing to increasing. And then just to add a little extra note on that, one way of finding the vertex is to do the opposite of b divided by 2a, and then you'll plug that result into your quadratic to solve the y value. And that is one different way to solve for the vertex for those that are interested. So again, that's the lesson summary. That's at the very back. That's on page 179. So now we're going to kind of go backwards, and we're going to talk back to the opening exercise, where they want you to consider in this opening exercise, if I had different mirrors, one that's a straight mirror, one that's a 90-degree angle mirror, and one that's a curved mirror. They want you to sketch how you think the light would reflect. Let's say we shot a laser light into each of these mirrors. How would we expect each one to reflect? So the first one is kind of the obvious one. We would expect this light to go straight into this mirror, and we would expect it to come straight back out. That would be expected. Now, with this other one, we don't expect it to do the same thing. Because it's going to come in, and this is an angled piece and not a flat piece, we expect this line to come in, hit this mirror, and it's going to go 90 degrees in the other direction, hit that mirror, and then go up. Each one would do the same thing, but either way, every single light that would go in would go down, bounce 90 degrees, go 90 degrees, and come back out. It would always be based around 90 degrees. This is where the curved mirror is of interest. So for the sake of idea, I'm going to put a a point right here. We'll call this the focus. And so if I have that focus, and let's say I had a line that was going to come into that focus, it's going to come down, hit that mirror, and the whole purpose of that focus is that's where that's going to go. If I did this again, let's say I took this one and I went straight down, it would bounce back up and go into this focus. Now let's say I added another one that's not here, and that comes straight down this way and bounces here, then it's going to go into that focus. What you're going to see with this mirror is that as the angles, as the rays get closer and closer to hitting the inside of the curve, the magnitude of the angles are going to decrease. And so the interesting thing for the curve, or any parabolic curve that we're going to study today, is those rays that come in, every single angle is going to be different and unique for that particular ray coming in. And the ultimate goal is to have all those rays focus in on know where, on how to utilize that point to make that work out. As we go through the pages of this section, they're going to show us some images. This one is of a telescope design. It's a reflector telescope, and again, this is designed by bringing light in, and that light would reflect on that angled mirror and then go into the viewing lens. We're not going to focus on this, but if this is something that interests you, then by all means take a minute and read the 2 bulleted points on that idea. So the next thing that the text shows is this figure right here, where again they emphasize the definition of a parabola, such that it has a directrix L and a focus F, set of all points so that they're equidistant from point F to line L. And again, so they're telling us that if we read the figure to the right, that FP1 would be equal to PQ1. And if I was to take a look at FP2, that one would be congruent to P2, Q2. And if I had this one out here, this one would be equal to this line here. And so this is just continuing to emphasize that level of congruence. We're emphasizing that because we're going to use that, like I said, again, we're going to use that coming up in a few minutes with the use of the distance formula, the difference of the x's squared plus the difference of the y's squared. And we want to be able to use that to rewrite this into a y equals ax squared plus bx plus c to be able to find the equation for this curve. That's what these pictures are reminding us and setting us up to do and see. The next image that you'll see in the notes is just a re-emphasis that every single ray or signal that goes into the parabolic curve is going to meet at a given focus. And again, if you look at the angles, here's one angle, here's another angle. If I come further into here, you can see this angle is definitely smaller than the ones that are out here. So as you go in, the magnitude of that angle decreases of what it needs to be able to do to rebound and make connection with that particular focus. The next several images do the same thing. Here's our curved mirror. They're showing us that every single time different line segments reflect with one endpoint on the curved mirror, and then there you have the focus. Anywhere the light hits this type of parabolic curve, it always reflects to the focus every single time, and so that's something to note. Here's another image that does the same thing as well, but they're adding the lines for the directrix to meet in there. That this line here, A, is congruent to this line A at the bottom, so this one is congruent to this one is congruent to these two, and so on as you go around the curve. So now, where does all this go, and what do we do is we're focusing on being able to take a look at this first example. It's going to give us a little bit of information in that design such that they tell us that the focus is at 0, 2. So that's right here on this image. And we have a directrix which is set at our x-axis. And so that's going to be denoted here on this line at the bottom. Now this time they purposely set our directrix on the x-axis. So we'll focus on that first, and in our next example, we're going to look at one where the directrix is not on the x-axis so that you can see the difference. And so what they do when we work through this is they tell us, as of a set of directions, let A be any point x comma y on the parabola. So they're going to choose this random point. This xy could have been anywhere on this curve, and this problem does the exact same thing. So they tell us that. They say let f prime be a point on the directrix with the same x coordinate as A. In other words, they're telling us let this go vertically down until it reaches the axis. This line is going to always be a vertical line that we're going to utilize. And so if that's given the case, they want to know what is the length of AF prime, this length from here to here. And so with a little bit of thinking and thought, the goal would be for you to be to say, oh, that is nothing more than the distance of y. Because if you stop and think of a rectangle on both sides, right? So here would be a horizontal line, this would be a horizontal line, a vertical line, and this, so you have your rectangle. This side would be equal to this side, and this would be the measurement of how far you go up on the y-axis. And so we can define this value as y. Now again, the reason why that's necessary, the whole secret behind this, is if you've been paying attention, we note that this line is congruent to this line. So I know a secret, that this distance is also y. That is what's going to allow us to go to our next part. So AF, we'll make this note right now real quick, AF prime is equal to y, which is also equal to AF if we want to make that note as well. They're both equal to y. Now it says use the distance formula to create an expression that represents the length of AF. So remember, we talked about that in that design. Let's get rid of that. There we go. And so we said that the distance formula for AF, the distance of AF, would be equal to the distance between the two. So we would have x minus 0 squared, and then plus y minus 2 squared. And then here we have our radical for the whole thing. And so this would be what will allow us to find the distance of AF. Now, looking at that and focusing on that, that's going to take us to page 177, where they're going to tell us to create an equation that relates the two. So we're going to move this out the way real quick. We'll enter this, get rid of that, move that there. And so here's where we left off again. We said that AF, whoops, we're clicking on all kind of things today. So we said that AF is equal to x minus 0 squared plus y minus 2 squared with a radical. Remember, that's this distance right here that we're calculating. It's this one right here. This is our points and our points right here, x and y and 0 and 2. And remember, we said that this distance is equal to this distance. And we had said, since this distance is y, then this distance here is y. So we're going to substitute out. If we know that AF is equal to y, we're going to say y equals, and then we're going to have all of this information, the x minus 0 squared plus y minus 2 squared with a radical. So we're going to simplify. We're going to solve for x. Now, to remind you our goal, because it's important to note our goal. Our goal is to write an equation of y equals ax squared plus bx plus c to describe the curve of this line. That's our goal. And so basically we're just going to solve for y. So to do that, we're going to square both sides. So now we get y squared equals, x minus 0 squared is x squared. And if we were to take this y minus 2 and go ahead and multiply it out and square it, we would end up with y squared minus 4y plus 4. So we're almost to our target goal. We know that since there's a y squared on both the left and the right, this one and this one can go away, so it becomes irrelevant. We can add 4y to this side, so now we get 4y equals x squared plus 4. And if we divide both sides by 4, we get y equals 1/4 x squared and then plus 1. That's the equation for this given curve. Now, one of the neat things to observe and think about, and the question didn't ask this, but this is neat to think about, is this here serves as a y-intercept. This c value always serves as the y-intercept. So that would make this point right here 0, 1. Now remember what I said about the line from the focus to any given xy, and then go directly down to the vertex. I mean, not the vertex, but the directrix. Those are always congruent. Well, it turns out that this distance here and this distance here does the exact same thing. So this is congruent to this one here. And so kind of a neat idea, if you know the focus here, if you were to divide these values by 2, you would get that vertex as well. So it's just a neat little thing to observe and note in this design. Now this creation of an equation for the curve is what we're focusing on in this particular lesson. So let's kind of recap here. The reason why this worked the way it did is because, remember, our directrix, we'll make a little note, our directrix was on the x-axis. And so we were able to say the distance from this point down to this point is this y value. It's equal to y. Even though we may not know the distance numerically, we know the distance represents whatever vertical distance we're going up on the y-axis. And again, we note that the line from this point to the focus is always equal to that line. Now that's going to become an important note with this y value as we go into example number 2. We're going to do the same thing, but like this time with a slight little twist in the design. So we're going to actually skip to exercise 2. We're not going to do exercise 1, it's not necessary. And we're going to walk through the same idea. So in this one it says we're going to derive an analytic equation of a parabola given the focus of 0, 4. So we can note that. Here's our focus. It's right here at 0, 4. And we have a directrix at y equals 2. So we'll note our directrix. And that is at y equals 2. Now that's important, because that's going to make a difference in how we're going to set up our equation. So in part A, they tell us to label a point xy anywhere we want on the graph. Now, we want to be very literal in that. They want us to label xy somewhere on the graph. So we're going to choose this point. Even though we know this point is at 2, 4, that's not going to help us in our endeavor. So we are going to label this point literally x, y. We're going to need that to be able to write our equation for this quadratic curve. And so in part B, they say write an expression for the distance from the point xy to the directrix. In other words, they want to know what is the distance from here to here. And again, if you say 2, that's not what we're looking for. We're not counting the squares to get an actual number. Now, this is where you have to be careful about. Think about what I said in the last example, where we had a vertical distance of y. Well, if you said that this here was equal to y, that would not exactly be correct this time, because the distance y is going to go all the way down to here, because this down here is the x-axis. So if you look at the green line that we have here on the side, I'll color it in a little bit better. We'll try to. and then you compare it to this orange line right here, the orange line is definitely shorter than the green line. So if the distance from the point to the x-axis is y, from here all the way down to here, then there's no way that that orange line can be equal to y because it's smaller. So you have to ask your question, by how much smaller? By 2 squares less. See, there's a difference of 2 squares. And so this orange line here is actually y minus 2. That is how much smaller that value is. So the answer to part B is y minus 2. Now, the reason why that's significant is because we now know this. Remember, we said that if we have a line from the focus to any point xy, and we drew it from that xy directly to the directrix, then this line has to be congruent to this line. So we now know that if this part right here is y minus 2, then this distance right here is also y minus 2. That's going to be our ultimate goal to figure out. So now they want us in part C to write an expression for the distance x from the point xy to the focus. In other words, they want us to fill in what this length would represent. And so that distance, and since I didn't label this, we'll just call this point A. And so we would say that the distance for AF would be equal to the same idea, x minus 0 squared plus y minus 4, because remember this point here is 0 comma 4, so you'd have y minus 4 squared in this goal. So now we're going to use that knowledge and that information that we have to be able to apply in part D. So that'll be next. We want to be able to apply in part D to find the equation that's going to make that work. We're going to take this off because we're not going to discuss that in any capacity whatsoever. Let's not do that. There we go. And so again, here's where we left off at in this whole idea and this whole thought process. We just said that AF was equal to x minus 0 squared plus y minus 4 squared with a square root. And to make sure we're all on the same page, remember when we did this on the previous slide and we found this, we said this distance was y minus 2, so therefore this one has to be y minus 2. So we're going to replace AF with y minus 2. And so now we carry all of this over. And so we have x minus 0 squared plus y minus 4 squared. And we're going to do the same process. To get rid of the square root, you square both sides. So when we square both sides, this side is going to yield y minus 4y plus, or y squared, minus 4y plus 4. The radical goes away. We can simplify some of this already. So x minus 0 squared is x squared. And then y minus 4 squared would yield us a y squared minus an 8y plus a 16. Our goal is to solve for y. Again, the same neat thing happens. This y squared and this y squared is going to cancel because they're exactly the same on both sides. And so we'll start moving things around. If we add 8y to this side, we're going to get positive 4y. If we minus 4 to this side, we're going to get x squared plus 12. And if we divide by 4 on both sides, we get y equals 1/4 x squared and then plus 3. And so that would be the equation for this one. Now, does that make sense? Yeah, sure it does for this one reason. Our y-intercept here, or our vertex, is at 0, 3. This equation is translated up 3 units from the x-axis. And so we see that process starting to occur in that design, and that makes sense for that equation to do that in that design. So that's the goal of this particular lesson. With the rest of your time, what I want you to focus on is looking in the problem set, and in that problem set, I want you to take and look at these particular numbers. So we'll clear the screen to here. And so in the problem set, this is for lesson 32, or not 32, but 33, definition of parabola. I want you to first focus on problem number 12, A through D. This problem does exactly like the two that I modeled in the video. So if you get stuck in it, go back and rewind and look at what you need to look at. And then I want you to look at 13A. 13A, derive an analytic equation for the parabola given the information that they have. And then I want you to look at number 14. All right, so again, if you have any questions, make sure you ask. If you don't finish this in class, it's not scheduled homework for the weekend. But whatever time you have left in class, this is what you want to focus on, is 12A through D, 13A, and then 14.